Okay, continue. Last time I was doing the product and quotient rule, and now I must do the derivatives of trig functions. Paul's notes. All right. I got that window open. Just a tiny bit. All right. Derivatives of trig functions. Evaluate the limit as z approaches 0 of sine of 10z over z. Now, we know the limit as theta approaches 0 of sine of theta over theta is 1. We know that. So how will we use that in this context? So let theta equal 10z, then I suppose I can rewrite this as the limit as z approaches 0 of, rather, this. The limit as theta approaches 0 of theta over 1/10 of theta, right? Just going to make factual claims here. That's true, isn't it? Now, that obviously brings 10 up in the numerator. Or does it? Yes, it does. It brings... No, it doesn't. I guess I'm being foolish here. For some reason, it's just not working. Yes, really, sometimes I have to do this. Oh, yes, I thought so. Okay. And of course, A is sine of theta, B is 10, and C is theta, and therefore it's 10 times sine of theta over theta. All right, so just sometimes you doubt yourself sometimes. So I think it's just going to be 10 times that ordinary limit. I think it's that, but we'll soon see. Oh no, this one actually. Okay, that's good. As sine of anything approaches 0, that will be 0. And so this is approaching that indeterminate form of 0 over 0. And so I can just be honest and say I don't know that. Better look and see if there's anything even closely resembling that. Oh, there is. Darn it. All right, so we have to let's scan this one. This isn't the relevant one, but this is fine. All right, that we can do. That's fine. Right. Right then, we'll break it up. And we'll say it's the limit as alpha approaches 0 of 12 alpha over 1 times 1 over sine of 5 alpha. Then we'll multiply the entire thing by alpha over alpha. And this, the limit as alpha approaches 0 of sine of 12 alpha over alpha times the limit as alpha approaches 0 of alpha over sine of 5 alpha. So for the first one, we can see that it's going to be 12. And for the second one, I do not see how it is not simply 1/5. And thus it's 12/5. But we're about to see. No, we should confirm. We should think. Okay, let's think. Got it. That becomes that. X over sine of 7x becomes 1 over that. And that we can actually do. So that'd be the limit is alpha over sine of 5 alpha becomes 1 over sine of 5 alpha over alpha. And so the limit as alpha approaches 0 of 1, which is exactly 1. And the limit as alpha approaches 0 sine of 5 alpha over alpha is exactly 5. So I do believe that it is 12/5. This one here works out to be the nice and tidy 3/8. Okay. Right. Back to it. Now we check. And we get the nice and tidy 12/5. Okay. Now, we are aware of the result that the limit as theta approaches 0 of cos theta minus 1 over theta is 0. We know that fact. And so, in this case, however, let theta equal 4x. Then the limit as x approaches 0 of cosine 4x minus 1 all over x becomes the limit as theta over 4 approaches 0, which is equivalent to the limit as theta approaches 0, of cosine of theta minus 1 over a quarter theta. Which is 4 times the limit as theta approaches 0 of cosine theta minus 1 over theta, which is 4 times 0, which is 0 itself, I believe. But we see what they did. For outside the brackets, right, like that. Okay. Suppose that's a better way. Right, okay. Now for the actual trigonometric differentiation problems. So f of x is 2 cosine of x minus 6 secant of x plus 3. Differentiate that. Okay, f prime of x going term by term. d by dx of cosine of x is minus sine of x, so it would be minus 2 sine of x. d by dx of sec x is sec x tan x, and so it would be minus 6 sec x tan x. And the 3 is the constant rather disappears. G prime of z. G of z is 10 tan of z minus 2 cot of z. So what is G prime of z? d by dx of tan x is d by dx of tan x is sec squared x. d by dx of tan x is sec squared x. So d by dx of tan z is sec squared z. So tan sec squared z d by dx of cot x is minus cosec squared x. So d by dx of cot z is minus cosec squared z. So that would become negative, and the double negatives cancel out, and so it'd be plus 2 cosec squared z, I believe. But we'll soon see. We compute, and that's correct. We've computed, and that's correct. Now, d by dx of sec x tan x is sec squared x. Isn't it? No, it's not. That's not right. Wrong. Wrong. This is to mislead me. Get it straight. All right. To review one more time. d by dx of sine x is cos x. d by dx of sec x is tan x. d by dx of tan x is no. Keep jumbling those up mentally, right? Just one more time. d by dx of sine x is cosine x. d by dx of tan x is sec squared x. d by dx of sec x is sec x tan x. That's it, correct. Then d by dx of cos x is minus sine x. d by dx of cot x is minus cosec squared x. And d by dx of cosec x is minus cosec x cot x. So in this case, they're trying to trick me because that's not on the standard results of derivatives. So what am I to think here? Okay, I'll break it down into definitions. So I'll say that f of w, by definition, no, wait, I can just use the product rule. Okay, I can just use the product rule. But let's also just say what it is by definition then. So that's sine w over cosine w, and that's 1 over cosine w. So that's sine w over cosine squared w. So if I was really in trouble, I could do this. Nonetheless, we are going to use the product rule. Okay. So differentiate the first one and leave the second one alone. Then differentiate the second one and leave the first one alone. So that would be that plus that, I believe. But now we have to check. Okay, good, that's correct. Problem 7, term by term. So h prime of t is 3t squared Then the product rule is applied to t squared times sine of t. So I'll do a big minus sign here. Differentiate the first one. Leave the second one alone. Differentiate the second one and leave the first one alone. Just like that. Now for the eighth one. Okay, so dy by dx is the constant vanishes, and then we have to apply the product rule to this, and that is 4x to the half. So differentiating the first one, we get that, and we leave the second function alone, and then differentiating the second one, minus cosec x quad x. So it'll become this, and then of course you want that to be more aesthetic, I suppose. So that's like that. And that should be okay, right? Okay, ninth one now. So it's really the quotient rule, isn't it? Except the top function happens to be a constant function. So r prime of t should be f prime g minus f g prime all over g squared. So f prime is, well, it becomes nothing. So f prime of g cancels out. So minus f g prime. So we have to find the derivative of this denominator here. So that would be then that, then this has to be squared out. Now I don't doubt when I square this out, I'm going to get something. I don't doubt when I square this out. It's like a rhyme. Okay. So we have 4 sine squared t plus 4 cos squared t on the base, which amounts to being the number 4. But then we have 12 cos squared t left over. Do they want this in a simpler form? Because it seems as simple as it gets when it's like that. We'll just glance. And apparently no. That's as simple as it gets. Okay, quotient rule. F prime g, so derivative of that is 1 plus sec squared v. Minus f g prime derivative of cosec v. d by dx of cosec x is minus cosec x squared x. So and all of this over this. Okay. Are they serious? All right, just think. So we have 1 plus cosec v plus sec squared v plus cosec v sec squared v. Then what? Plus that Now, I don't know about you, but that seems pretty complicated looking. So, first of all, they cancel out. Okay, anything else? Well, sine squared x plus cos squared x is 1. Dividing through. No, that's not going to help us. All right. On that one. Well, cosec v, cot v, that's cos v over sine, and that's 1 over sine. So nothing simpler happens there. That's just 1 over sine. I don't see how anything at all becomes simpler here. I really don't. No, you just have these two that you can add together, and that's really it. Do not see how anything at all can become simpler, except for that. And then you have this down here in the denominator. So we have to glance. Nope. You actually just get this monstrously complex looking thing here. But I suppose if that's what they want to do, that's what they want to do. Right, okay. We'll bracket that just to indicate that this is just sort of, we're just thinking about it. But there's nowhere to really go with that. It's as simple as it gets. Find the tangent line to f of x at x equals pi. First, f of pi is tan of pi plus 9 times the cosine of pi. And what is tan of pi? Well, that's 180 degrees, is it not? And therefore 0. And what's cosine of pi? Well, that would be -1. So that would be -9. Thus, pi comma -9 lies on the line. Then f prime of x. So d by dx of tan x is sec squared x. And d by dx of cos x is minus sine x. Just like that. Then we find f of pi to get how steep the tangent line actually is. So sec squared of pi minus 9 sine of pi. The secant function is 1 over the cosine function. So 1 over the cosine of pi all squared. Wait, what's cosine of pi? Oh, that would be -1. And then you must square it. So we get 1. And what is sine of pi? Well, that would be 0. Isn't it? Yes, it is. It's 0. So it's just 1. So now we use y minus y1 equals m times x minus x1, because that will let us get the formula for the line. And we just plug stuff in. So y at 9 equals 1 times x minus pi. So y equals x minus pi minus 9. And there you go. That should be good. But we must check. Everything must be checked. Yes, y equals x minus pi minus 9. That's great. Okay, problem 12. The position of an object is given by s of t equals 2 plus 7 times the cosine of t. Determine all the points where the object is not moving. So if that's the displacement function, we need to differentiate it to get the velocity function. And then ask the question, where does the velocity equal 0? So s prime of t, that's me differentiating it. Constant disappears. This turns into this. Then when does s prime t equal to 0? Like, when is this equal to 0? The sine function is equal to 0 when t is 0 itself, or you just add on pi over and over again in either direction. But because negative time is not seen as sensible, you just say pi n like that, or n equals like that. And that should be good. But we'll soon see. Okay. Right, so they asked the same question that I did. And to them, wait, why is it not? Or is this just the same and I'm just not seeing it? If you plug in 1 here for n, no, sorry, plug in 0 here for n, you will get pi, which I agree with. Why is it not 0? Why is 0 not okay? Strange. Oh, right, okay, so they allow plus or minus. They allow the plus or minus business. But I thought that wasn't okay because we're dealing with time, aren't we? All right. Problem 13. Where in the range from -2 to 7 inclusive is the function f of x equals 4 cosine of x minus x increasing and decreasing? So we must differentiate and then find out where the derivative is positive or negative. Okay, so when you differentiate cosine, it turns into minus sine. So minus 4 times sine of x. Differentiate that, it'll turn into minus 1. And now we have the derivative. Find out where it's positive and where it's negative within that range. Okay, so because that range is quite close to the origin, I think you can just graph it Or is that the best way to do it? Let's just find out where we get zeros within that range. And because the sine function oscillates back and forth, we'll be fine then. So move the 1 over, divide by the -4, and we get a quarter. And when is that true? Well, inverse sine of a quarter. And then so we get 0.252, 0.2527. But then we have to get it in range. So add on pi. (3943) and add on pi again. (5359). And if you add on pi again, you'll get out of the range. But wait a minute. Did I take away pi enough? Okay, when you subtract pi from here, you get -2.8889, and so that's outside of the range. So I think it's just these that apply. And now we need to figure out if the derivative is positive, and where it's positive, rather. So here's what I'm picturing. Picturing -2 is there, and 7 is there. And then 0.2527 is there. 3.3943 is there. And 6.5359 is there. And it'll do a plus minus pattern somehow, but I need to be sure, and I need to pick something. So I'm going to pick x equals 1. So I'll do -4 times sine of 1 minus 1. And I get a negative number, and therefore here it's where 1 is, it's decreasing. And so it must be decreasing here. And so it must be increasing here and here. And then we declare that fact. And we say that the function is increasing from. Now we have to be sensitive about the fact that they actually include -10, -2, and 7. So what do I say? I say from there to there, and then from there to there, but I don't be inclusive about those. And the reason why I don't include the borderlines is because that's where the f prime of x is 0. And so the function's neither increasing nor decreasing there. And then decreasing would be for the other ones. So I think. Like that. And then one more. Like that. Now we check. Okay. So he agrees. And he agrees. Uh-oh. Check this out. He does not have the same number that I have. How can that possibly be? What? All right, so these two numbers agree, but not the 6.5-ish one. How on earth is that possible? Okay, so let's just do minus 0.2527 plus pi. And we get 0.2527 plus pi. That's how we get that one. And then you add pi again. And that's how I got that one. So what the hell is... All right, that's a minus sign there. I am definitely not thinking this through straight, am I? Okay. All right, so first problem is that we have this. Right, I agree about that. Put a plus 1 over there, and that should be minus a quarter. Right, so there's my first problem. I dropped a sign, a minus sign. And okay, so I agree with them about that. That should be a minus sign there. And then there's another solution, isn't there? The other solution is negative pi, but it's that distance away. So that's when we get the 2.8889 thing. And then we have to add on pi. Or add on 2 pi, rather. Okay, that one being negative makes sense. That one is another solution. And then it would be 2 pi minus the difference between 0 and this, which is 6.0305. Right. So there. There. And there. And that's cleaned up now. Okay, that's good. All right. Save. And move on. Next up, derivatives of exponential and logarithm functions. All right, let's see. Okay, great. Okay, what's the derivative of this? d by dx of e to the x is e to the x, and d by dx of a to the x is a to the x ln a. So we use those standard results, and we try. Like that. So I don't know if they'll want approximations, but we'll see. All right, that's good. Next one. d by dx of ln x is 1 over x. d by dx of log base a of x is 1 over ln a all times x. So this one here should be that, and this should be that, logically. And that's okay. That's good. For the third one, there's r of w, and now computing r prime of w. So that's a product. So we differentiate the first one and leave the second one alone. So that would be ln 3 to the w, differentiating the first function, and you leave the second one alone. Then differentiate the second function and leave the first one alone. The derivative of log, this is log base 10, log base 10 of w, and therefore it's 1 over ln 10 times w, or 1 over w times ln 10. That would be better. Like that. Okay, so check. Looks good. All right. Fourth one. dy by dz. Let me see. What would that be? 5z to the 4. Then product. We have a product here. So I'll do a bracket. Differentiate the first, leaving the second alone. Differentiate the second, leaving the first alone. So it would be e to the z over z. Okay, so if they want any kind of simplification at all, we could extract out that factor, but then everything becomes a minus, so just have a minus there, like that. And then ln of z plus 1 over z, like that. And that looks pretty. There you go. All right, so that's correct. So, fifth one. H of y is y over 1 minus e to the y. So we have a quotient to differentiate. So let's do it. F prime g minus fg prime all over g squared. So differentiate the top, leave the bottom one alone. So we're just going to have this minus sign. Differentiate the bottom, leave the first one alone, leave the top alone rather. So when we do that, we get minus e to the y. So minus e to the y times y. So minus y e to the y. So plus y e to the y. And then square the bottom. So probably they want something fancy. But how to do that? Maybe that. And then I'd leave the bottom alone. Although it would be e to the 2y. Nope, just leave it alone. And that's fine. In my eyes, that's fine. Yep, the same thing as that step there. Problem 6. F of t is 1 at 5t all over ln t. So we have another quotient. So we better get to it. F prime g minus fg prime. So differentiate the top, leave the bottom one alone. So we will have 5 ln t. Then a minus sign. Differentiate the bottom, leave the top alone. What's the derivative of ln of t? 1 over t. Leave the top alone. And square the denominator. And there you go. And what would that be? 5 ln t minus 5 minus 1 over t. And there you go. And we check. Everything must be checked. And that's correct. And that's good. 7. Find the tangent line to f of x equals 7 to the x plus 4 to e to the x at x equals 0. So first, compute f of 0. So we get 7 to the 0 plus 4 times e to the 0, which is 1 plus 4, which is 5. So 0, 5 lies on the line, lies on the tangent line. Then f prime of x, 7 to the x, when you differentiate that, you get ln 7 to the x. For e to the x, when you differentiate that, you get 4e to the x. Compute f prime of 0 to find the gradient of the tangent line. So ln of 7 times 7 to the 0 plus 4e to the 0. So that's just going to be ln 7 plus 4. And now y minus y1 equals m open brackets x minus x1. So we have x1, y1, they are 0 and 5. So we say y minus 5 equals ln 7 plus 4 open brackets x minus 0. So y equals ln 7 plus 4 x plus 5. And so I believe. But we must check. Everything must be checked. And that's right. That's right. And there's the approximation. Next, find the tangent line to f of x equals ln of x log base 2 of x at x equals 2. So it's very similar to problem 7. First, f of 2. To find a point on the tangent line. So it's ln of 2, which is like 0.693691, something like that. Then log base 2 of 2. To what power must 2 be raised in order to get 2? The answer is 1. So it's literally just ln 2. So 2 comma ln 2 lies on the tangent line. That's true. Now, f prime of x. So we have a product. So we differentiate the first function, leaving the second one alone, and then differentiate the second function, leaving the first one alone. So differentiate the first one, so we get 1 over x. So log base 2 of x over x. Then differentiate the second function, leaving the first one alone. D by dx of log base 2 of x would be 1 over ln 2, 1 over x times ln 2, 1 over x times ln 2. Right, so just like that. And now compute f prime of 2. So we get that. And then ln of 2 over ln of 2, which cancels out to be 1. And then, wait, what am I doing? That's a half. And then ln of 2 over 2 ln 2, so a half as well. So 1. So 1 is its gradient. Then y minus y1 equals mx minus x1. And y minus ln 2 is 1 times x minus 2. So y is equal to x. And then you have minus 2 plus ln 2. And that should be good. But we have to check. Everything has to be checked. Great. Okay, that's correct. Okay. Determine if v of t, which is equal to t over e to the t, is increasing or decreasing at these points. To solve that, we must differentiate v. So v prime of t, that's the quotient. So the quotient rule is rather f prime g minus fg prime all over g squared. So top, bottom, f prime g minus f g prime all over e to the t squared, so e to the 2t. Then what is v prime of negative 4? E to the negative 4 minus, or rather plus 4, e to the minus 4 all over e to the minus 8. Whatever that happens to be. And we compute. And we get 272.99. And so it's increasing. Part B, you stick in 0, and that we can actually compute e to the 0. We'll just say what we're doing first. So e to the 0 is 1. That's 1 over there. So 1 minus 0. So 1 on the top over 1 on the bottom. So 1. So it's increasing as well. Or so I believe. And then for 10, e to the 10 take 10 e to the 10 over e to the negative 20. 20 in that spot. Ten in that spot. 10 in that spot. And 10 in that spot. And we get something like that. So I think it's increasing for all of those, what we're about to see. Okay. Okay. That's trouble. Okay, so I didn't differentiate this right, did I? So what did I do wrong? Well, factor out e to the t, and then we get 1. No, that's actually fine. That's actually fine. I just didn't even realize it. Did I? Wait, what's the time? Okay, the time is that. And so that. And so that. So we agree. We agree. But why did I put this in? Oh my goodness me. A minus sign. One single symbol. That's it. Catching errors is one of the most important things ever. Decreasing. Brilliant. Okay, last we have g of z, which is z minus 6 all times ln of z. So compute the derivative. So g prime of z. Well, that's just ln z minus plus sign rather, plus sign. Z minus 6 all over z, just like that. And of 1. So can I do this myself? That'll be negative there for sure. And ln of 1, to what power must e be raised to get 1? The answer is 0. So 0 plus 1 minus 6 is minus 5 over 1. So minus 5 over 1. So decreasing. Ln of 5 plus, would that be negative 1 on top? So negative minus a fifth. Which is surely greater than 0, so increasing. G prime of 20. Ln of 20. So somewhere between 2 and 3, something like that. And then 20 minus 6, that's 14. 14 over 20 is 7 over 10. And that's surely greater than 0, and that's surely increasing. And then we check. And that's correct. That's correct. And that's correct. And that's good. Be well.